Hey, what's up? Can you hear me?
Yeah, I can hear you.
Hey, how you doing, man?
Doing good.
Cool, cool. Did you have a chance to read any of the book, or are you just reading along with us today? Or?
I ordered the book, but like it's not yet come.
Okay, nice, nice. You actually got the hard copy, huh?
I kind of like my Kindle is not working, so like I usually like either Kindle or I'll buy a hard copy. Like I recently bought the hard copy for system design interview, so I thought that I'll buy the hard copy for this as well.
Uh huh. Uh huh. Nice, nice. Cool. Yeah, it's nice to have it. It's just that the stuff becomes outdated so quickly when they come out with the next version. It's like, now what? But it also is nice. That's one thing that I value above everything else is my my bookcase. you know. So
Yeah, true.
what's up? What's up? We got a decent amount of people flooding in here. Feel free to unmute and just introduce yourself. Let everyone know where you're from. We can start at the top. We got a. Let's see. I guess we'll just start with introducing ourselves, your name, your location, how long you've been coding, and then what interests you about machine learning, and then we'll move on to the next person. It's 6:02 right now, so we'll just start going through that phase right now, just to give you a little idea about what we're going to be doing here. Is we decided last week that we were going to actually be reading through the book. So we're going to be taking our time. We're not rushing through it. We're reading through the book. Um, Hopefully everybody has read the first chapter before coming today. If not, it's fine. But if you don't have a background in machine learning, then it might be a little difficult to partake in the conversation, which is okay. But it's nice. I would say if you haven't read the first chapter, make sure you read the chapter by next week. That way, discussion will be much easier. We're going to be working through the second chapter today. So it's an end-to-end machine learning project. I believe there's some linear regression. We're going to be using a real estate data set. So we're going to start from the top of the chapter. We're literally going to read through it together. Have your code editor open. I'm using PyCharm on my end. I'm new to it, so I'm going to be taking my time with PyCharm as well. Typically, I use Visual Studio Code. I'm using like JavaScript or C, but I'm newer to Python, so this is going to be cool for me as well. And yeah, we're just going to work through the chapter piece by piece. If we encounter lingo that we don't understand or someone doesn't understand, then maybe someone here already understands the lingo and can explain it. If they don't, then someone can do a little bit of research, do a Google search, and as we continue reading, they could do that research, and then at the end of the next paragraph, they could kind of like share what they learned, or we could all stop at the same time. But the big point here is we're not rushing. We're moving through the book slowly. For those who are like, hey, this seems really slow paced for me, if you go to, that's totally fine. Two, we don't expect this to be a format that's perfect for everybody. You can't make everyone happy, and that's okay. But if you go to the top of, let me share my screen really quickly. So I just shared my screen. If you go ahead and double click my name, we're all in the machine learning channel right now. And if you double click my name, you'll see my screen. I'll just give everyone a minute for that. So double click my name. Now, if you go to the top left here in the welcome section, you see choose a location and choose a specialization. If you go ahead and you can see machine learning is the brain. If you click on this brain right here, then it's going to give you access to channels that you won't see otherwise. So if you click on that brain right there, if you're just like, hey, this is a little slow pace for me, it's totally fine. Click this brain. And then if you go down, you'll see we have our specializations. Now, you're not going to see all this unless you actually click every single one of these. You'll just see the ones that you click. So if you're interested in software engineering, machine learning, and like distributed systems, and you click each one of these, then you'll see those three channels under the specializations tab. And that's so the people who just want to move at their own pace, who are like, hey, this is kind of dragging. I kind of want to move through it. This is a little slow for me. We still want you to be able to share what you learn and partake in the discussion. And so we have this machine learning channel right here. And hopefully as we push through the book and more people join, it becomes busier and busier and all that. So yeah, we'll start from the top. Typically we have people trickling in until about 6:10, 6:15. So I'll just start and then we'll work our way down. Everybody can introduce themselves. If people can't hear you, it's probably because you have your microphone muted. At the bottom left, there's a mute button. So just click that and you should be good to go. If you're unmuted and it's still not working, then you're probably going to have to go to user settings. Click on user settings, voice and video, and you'll have to change your input device to match the input device that you're using. If it's still not working, I'm not positive what it is. You're probably going to have to just do a little bit extra troubleshooting. So I'll start. I'm Jim. I'm from Connecticut. I've been coding since about 2017. I don't do it full time. I'm actually in sales management. I sell solar energy. But I spend a few hours every single day coding. Back around the time of COVID, I was looking for an in-person meetup and I couldn't find one anywhere. And so I just started hosting my own. And it just grew week after week. It just continued growing and growing. And I was totally surprised because I went to a free code camp meetup that was a weekly meetup before COVID started. And eventually it grew to a size that was larger than any of the free code camp meetups that I've been to. Yeah, we can hear you.
About me, bless.
So yeah, and then one of the guys started recommending, start the Discord, and we started doing like data structure algorithm competitions and trainings and JavaScript and other stuff. And so we decided to start sharing it with people outside of our local area. So that's my story right there. Recently, I've been interested in machine learning. I've been doing my own research on it. So I was like, hey, this is something tons of people are interested in. Aditya has been to a couple, and Alex has been to a couple of our other events. It looks like everyone else is pretty new, but welcome. And yeah, thanks for coming. Aditya, you want to go ahead, and then we'll work from the top to the bottom?
Yeah, sure. So my name is Aditya, and I'm in Florida. So I've been coding I did my bachelor's back in India, and I graduated in 2018. So you could say I'm coding from like 2014, but like not like work coding, but I have like around 3 years of experience, in software development, like professional experience. And this channel basically also helps me to like focus on broaden my like zones, my software development zones, because machine learning is kind of like a software development as well. So I feel like this helps me like learn some more like different areas as well, apart from just software development. So yeah.
Awesome. Welcome back. Alex, what's up? Can't hear you, Alex. It might be something with the mic on your end. We'll move on to Alan to keep it pushing, but when you figure out your mic situation, just shout out. Alan.
I'm here. Can you hear me?
Oh, yeah. Hey, what's up?
Yeah, sorry. I was like trying to put my thing on. Or switching something in the settings. But yeah, so I just finished a coding bootcamp myself. Been coding for about a year and a half, but everything was online. So kind of looking for like a more pure programming, kind of seeing how other people like their thought process and how they go about coding themselves. So yeah, it was primarily focused on Python. So I love that like there's a huge JavaScript thing, but seeing there's like machine learning and AI that I can continue with Python is kind of what brings me here right now.
Awesome. Welcome.
And I'm in New York City for reference there.
Alan Hastings, what's up?
Can you hear me?
Yeah. What's up?
Yeah. Yeah, I'm kind of coming over from the computer graphics world, which I've worked in for the past 35 years. Did a lot of visual effects software. Worked on the movie Titanic for a year. Did a startup called Lexology, making computer graphic software. But now I'm kind of thinking of shifting into AI, specifically like text to film ideas. So I'm just trying to basically train myself on the whole topic.
Cool, cool. Where are you checking in from?
I'm in Palo Alto.
Okay, awesome. Awesome. Welcome, welcome. Who is next? We got B. What's going on? I just see B, but it might be something else.
I think it's Bad Dogs?
There's Bad Dogs, but there's someone just above him as well. There's a picture. You got a green shirt on.
Yeah, that's
Byron.
Byron.
All right, Byron.
Oh, that's me. How you doing? Coming out of from Chicago. I'm just getting my feet wet with machine learning. I've been kind of tinkering with computer vision lately, and I'm using a lot of C#. Did some embedded coding and whatnot, and I'm here just to kind of learn a little more about machine learning and kind of network with other people.
Awesome, awesome. Welcome. Bad Dogs, what's up? You might have to hook up your mic in the settings. So Chippy, what's going on?
Yeah, my name is Brian. I'm coming from two places. I moved out here to Atlanta like 6 months ago, but I'm originally from Vegas. I've been programming since like 2016, and I've been in the Python world. Never really actually did anything professional till this year. I'm a software engineer for the DHS, and I'm just trying to, learn a little bit more about machine learning. My current project right now is a way for OpenAI or the LLM to control your PC from the command line. And
Awesome, awesome. Welcome. Glenn, hey. Looks like you're muted, Glenn. Bottom left, you'll see a little microphone. You'll be able to mute and unmute. There you go.
Yeah, hi there. No, I was changing my avatar. So I missed part of it, but I think we're just introducing ourselves.
Yep.
So cool. I'm Ken from Texas, and I have a master's degree in cybersecurity and an engineering undergrad degree, and I do like AWS development, usually using JavaScript and Lambda functions. And I was just fascinated by this topic and enjoyed it. One thing I wanted to say was I found I don't know if everyone has a textbook. If I got a free log on to O'Reilly Books, and for 10 days I can read the book. So I don't know if anyone needs that info. They haven't bought the book yet.
Yeah, I don't. I was going to ask for the book link. So whoever has it would be awesome. Awesome.
Yeah, so as far as like a free copy of the book goes, I'm not able to find any free copy, at least any like legal free copies of
I don't mind paying for it. I have no idea what the book is. Like this is my first time in this one, so yeah, I don't know what the book is.
Yeah, let me go ahead and share the link.
And O'Reilly, and I can put a link in the chat once I find where that is. I haven't used Discord before. And I noticed, and this is for it's not like well, I'll just say it. There's like a third edition of the book.
Yeah.
There's a lot of updated stuff and updated examples. So since I can get any version, I was looking at version 3. Anyway, back to you.
Yeah, I'm gonna go ahead and post the link in the machine learning chat. So there you go. That's O'Reilly. That's what I'm using. But like Glenn said, you could buy it off of Amazon, eBay, Google Books, I think has it, or There's probably tons of other sources or like bookstores. I'm sure Barnes and Noble has it as well. O'Reilly is just easiest for me. I like it because you just always have the most updated versions of the book. Though you do get the 10-day free trial, and then it's $50 a month after that, or you could just pay, I think, $500 for the full year. Bad Dogs, is there a link to the presentation screen where we be presented? It's not a presentation, it's just a book club. We're working through the book together, so we'll be writing code together as we work through the chapters. If you want something a little faster pace, I'd say just work through the book on your own and then stay in communication with everybody through the machine learning channel. There's going to be a lot more conversation there as we continue hosting this week over week. But all right, so we have Hank the cow dog. What's up? Hank, you're muted. We'll hop to Herschel. What's up? Herschel, you're muted too. We have K just above Kevin. All right, we got Kevin. Welcome back, sir. How you doing?
Hey, is this the same book as the last time?
Yeah.
I think I've got the version 3 PDF.
Okay, cool. I personally wouldn't use random PDFs that people share with me over the internet, but I'm not the police, so y'all will do what y'all are gonna do anyways. Yeah, the only free versions I found that were like legitimate were version 2. But yeah,
I will check mine for illegitimacy.
I know you will. All right, Kev, you want to go ahead, introduce yourself, and then we'll keep moving down the line and get this show on the road?
All right. Well, I'm a, 20-something year programmer. I'm working for a company right now that I might want to be using AI for. And I've done, probably about a third of the languages out there, seems like.
Cool. Well, welcome back, sir. Mr. Torrance.
Yeah, hey there.
Hey.
My name's Russ. I got like 25, 30 years software experience. Mostly startups, some big companies too, all sorts of technologies, kernels, device drivers, web applications, security, whatever. Got a little sick of it a year or so ago. I haven't been working for a while, but then found my passion for AI. So now I'm just kind of training myself. Just started playing with LangChain and some of those tools and getting LLMs running on my local machine and playing with the quantization stuff. And so this seemed like right up my alley as I'm starting to dig into this stuff. Whether it's PyTorch or whatever.
Awesome. Welcome.
Thank you.
Nathan. Hey.
Hey, can you hear me?
Yes.
I am also from Atlanta, Georgia, well, just northeast of it. I'm a very long-term software developer. I have started a few of my own projects, and I'm looking for some of them to be machine learning. So that's why I'm here.
Awesome. Welcome. Reptar Ruler 007.
Hey, how's it going?
Pretty good. How you
my
doing?
name's Christian. Oh, hi, thanks. My name's Christian. I'm from Atlanta as well. Short-term software engineer. 4 years ago is when I started. I was a geologist before then for an oil company. Yeah, I'm just here trying to network and learn as much as I can. And that was my dog shaking.
Awesome, awesome. Shalab?
Yes, hi, I'm Shalab. I'm from San Jose, California. I'm in the industry for about 20 years doing mainly software QA, dev test for network protocols. I know C and some Perl, and I've learned a bit of Python, but I want to do more machine learning.
Awesome, awesome. Welcome. Victor.
Thank you.
Hey there, my name's Victor. I've been programming for a number of years, C# mostly. Recent years more so in doing project management, but looking to get into back into coding some more. And AI struck my interest, so wanting to learn more around that.
Cool, cool. Welcome. And then last but
Thanks for offering this. It's really cool.
yeah. Last but not least, WM. How are you?
Yeah, can you hear me?
Yes.
I've been software engineer for like over 20 years, way back with these, C and C++ and Perl, not for a while, mostly Java through most of that, and then some integration platforms, including this thing called MuleSoft. But I've been doing Python for about 6 years. Most of my home machines are Linux now. I built one, and then seems like I'll switch my laptops over to that since then a little more. I mean, I've used it for 20 years on other machines. I've been interested in AI way back, even before Python was the language to use. So that's kind of a happy accident. I just want to learn more now. Seems like a good thing to pick up.
Totally.
The way
Totally.
things are going.
Agreed. Awesome. Well, welcome.
And I've learned enough to know that you're not going to train ChatGPT on your home computer without $1 million and a bunch of machines. Common early thought. But go ahead, I'll mute.
Cool, cool. Welcome. Thanks everybody for sharing. So I'm going to go ahead and share my screen and just give a little brief intro here about what we're going to be doing. So for those who are brand new to the server, our events are just at the top left. So you're going to be able to find all of the events each week. I'll update this on Sunday and I'll share an announcement. Hey, just posted the events for the week. If you want to choose a location, go ahead. You'll have location specific chat and be able to stay in communication with people in your area. And then same with specialization. If you're interested in AI, just click this brain right here and that will open up the machine learning channel for you. You'll be able to continue the conversation throughout the week. So if you're not able to make a Wednesday, or you realize like, hey, they're just working through the book too slowly, I kind of want to do this on my own, but I still want a community to talk to about this and learn together, this channel here is for you. So besides that, I'm going to go ahead and share the book that we have. So I'm using O'Reilly. I just think it just has so much content, almost too much. So this is the book that we're going to be working through. It's called Hands-On Machine Learning with Scikit-Learn, Keras, and TensorFlow. It's the go-to. This is the book that whenever you ask someone who's been in the game for a long time anything about machine learning, they're like, start with this book. So personally, I just started working through the classification chapter. I already finished this chapter 2 end-to-end machine learning project just individually, but it's gonna be nice to work through it with everybody else as well. So it's gonna be, if you're like newer to machine learning or programming in general, you're really gonna want to read the fundamentals of machine learning. You really want to read chapter 1, because chapter 1 is going to give you a really nice overview of just the landscape of machine learning, but it's also going to teach you some lingo that's important for the conversations. It's going to be hard to have a conversation if you're new to machine learning or programming and you haven't read that chapter. But we're going to be working through the end-to-end machine learning project, just from the top to the bottom, moving slow. If we encounter words or lingo that we don't understand, we'll go ahead go down the rabbit holes that are required to really make sure everybody's grasping it. We're going to be moving at a very, very slow pace, so just a heads up on that. And then, yeah, we're going to work through each chapter of the book just week over week, 90 minutes per week. But as I said, I'm still working through the book at my own pace. I'm spending a few hours throughout the week. Like I said, I'm like a quarter through classification. And even when I finish that, I'm going to keep working. So I'll finish the book probably months before we finish the book here. But the main benefit of this meeting here is really to work through it step by step, even if it's something you've already worked through, so that as we're working through it at the slow pace, we could really have a good, thorough discussion with other people who are also working through the book. So, does anyone have any questions before we get started? Actually, let me just go ahead. I'm using PyCharm. I'm newer to PyCharm. I typically use Visual Studio Code for like JavaScript or C, but I'm going to use PyCharm just to learn a different tool. And also, it just makes using Python easier, I think, as far as like setting up the VENV, the configuration of Python projects. There might be an easy way to do it through Visual Studio Code, but I decided to learn a new tool. So it's up to you what code editor you actually want to use, whether it's Visual Studio Code, PyCharm, Jupyter Notebooks, Google Colab, or one of these other tools. It's really up to you. If you don't have a code editor yet, I would say go ahead and just download and install PyCharm. And then work through it. I'm pretty sure the first thing we're going to be doing is we're going to be pulling data into our file, and then we're going to be analyzing, manipulating, changing data, creating a model that fits the data. Like, this chapter is very, very interesting. But as far as the plan for moving forward, working through the book slowly, and coding along and discussing simultaneously, does anyone have any questions on that?
I'm good with that.
Cool. Is there anyone who doesn't have a code editor?
I'm using Google Colab. I have a code editor, but like, I like when it's machine learning or something, like, for me, Google Colab is more comfortable.
Cool. Awesome. All right, then. I'm going to put the book on one side of my screen. I'm going to put PyCharm on the other side of my screen, and we'll start working through this chapter. I highly recommend that you code along. The reason why I'm actually coding along and typing code as we go through this chapter is just to get that muscle memory, actually practice typing the code. I'm going to be writing comments. I just recommend that, because even though you have the discussion, there's nothing like really actually typing out the code and getting that hands-on experience. So we'll start working through this chapter here. Feel free to unmute, shout out, ask questions. If I read this first sentence and there's something where you're like, what is a data scientist? Like, what actually is this? I don't understand. There's gonna be tons of lingo and words that we encounter. Just say, hey, I don't know what this is. I'm gonna go find out real quick. And so we'll continue reading and working through it, but when you find out, then you could come back and you could kind of break down what that is for everybody. So if you don't understand what one of the words are, there's definitely someone else who doesn't understand what one of the words are. So it's going to be nice for someone to just say, hey, I don't understand that. I'm going to go check and then come back. And this is meant to be interactive and be a high level of communication. So don't feel like you're slowing things down or you're disrupting. It's supposed to be, I don't want to be the only one talking, so feel free to just shout out, and as we work through this, stop, discuss certain things. That's what it's all about. There's meant to be discussion and pauses. It's not supposed to be just all reading.
Can I ask a question before you get started?
Of course.
or a warning or whatever, just in case it comes up. I found out several months ago when I tried to go through like the number, not this book, but like the number vision example where you get the digits, that my machine, which is an older, well, it's not old, but it doesn't support TensorFlow because of some CPU instruction set, so you had to use DNO and Keras. So if that comes up, it's going to try. I don't know what library this is going to get into this chapter, but I had a case where it just would not run because of my CPU. So I don't know what other people have. Just have you ever run into that before with anybody?
I haven't personally run into any issues with TensorFlow, but also you don't really start getting into TensorFlow or Keras until part 2 of the book, where you start getting into neural networks. The first part of the book, yeah, the first part of the book is mostly Scikit-Learn, pandas, NumPy, the popular Python like numerical and scientific libraries.
Hi, this is John. I've been doing this for a while.
Hey.
If you ever have difficulty with binary dependencies, like NumPy and Scikit-Learn sometimes run into, my advice is you're often much better off using Conda, or mini Conda, than straight pip. Conda is just better at complex dependencies, especially if you have a weird CPU.
Yes, Conda.
It wasn't a dependency. It was the CPU doesn't support the instruction set, and I can't remember what now. It was VTX, or I don't remember what it was. Something newer.
Actually, Anaconda is like pretty heavy. Instead, if you want, use mini Conda. Like I used Anaconda and it stops everything. It's better to use mini Conda if you're using it.
Yep.
Awesome. Thank you, everybody. So in this chapter, we're going to be working through project end to end. We're going to be working from not having a data set all the way to building the model. We're going to first be looking at the big picture. We're going to be getting the data, exploring and visualizing the data to gain insights. This is pretty cool. You get a picture of what the data actually looks like when you visualize it. Preparing it for the machine learning algorithm. We're going to select the model to train it. We're going to fine tune the model. This was actually a very interesting part as well. This is where I kind of slowed way down when I did it independently, just fine tuning the model, because there's a lot of information to know. And even just in these 3 steps, for me, it was, I feel like, statistic heavy, where I was learning a whole ton of new lingo that I didn't know before. So I really would just stop reading through the book and stop building the model and spend like a half hour or 45 minutes doing some research. Then we're going to present the solution, launch, monitor, and maintain the system. So for anyone who's interested in working with real data, sure, we're going to be doing this end-to-end project and building this project together. But if you want to work on data, just you have an idea for a project or want to build something on your own, these are a couple good spots where you can do that. And then, so in this chapter, we'll use the California housing prices data set from the StatLab repository. This data set is based on the 1990 California census. It's not exactly recent. A nice house in the Bay Area was still affordable at the time. That's funny. But it has many qualities for learning. So that's the data set we're going to be working through. So I like how they present it, just like, hey, you're working for the machine learning housing company. This is your first project. You're building a machine learning project to solve a problem for the company. The first task is to use the California census data to build a model of housing prices in the state. We're going to use this model to predict the price of a house based on the features of the other properties that exist in the data set. So this data includes metrics like the population of the area, the median income, so what people are making, the median housing price for each block in California. I'm not from California, but I'm guessing a block is just a certain square area of a location. Block groups are the smallest. Yeah, there we go. The smallest geographical unit for which the U.S. Census Bureau publishes sample data. So they typically have a population of 600 to 300 people. We'll call them districts. Our model should learn from this data and be able to predict the median housing price in any district given all the other metrics. So based on the other features of the house, like the number of bedrooms, the population, whether you're near water, based on that information, given that information for a new property, we should be able to predict the price of this new property. Got this tip here. Since we're well-organized data scientists, the first thing we should do is pull out your machine learning checklist. And I'll go ahead and navigate here just so we could check this out for a minute. Because from the research I did, this is a checklist that you're going to be going through with every single machine learning project. Regardless of whether you're building a neural network or using like linear regression, classification, or any model, you're going to be going through this same thing. And that checklist is this. We're going to be framing the problem and looking at the big picture. So really understanding the problem. We're going to get the data. And I hear that one of the greatest problems that people in the world of machine learning face is actually getting the data and having enough data to create an effective model. We're going to explore the data to gain insights, prepare the data to better expose the underlying data patterns to machine learning algorithms. Now, this is something I just want to comment on really quickly because before I started going through this book, this is something that I realized that I didn't realize before, is that there's actually a shape to data. Like there's a structure to the data. And based on that structure of the data, if we're able to determine what the structure of the data is, then we're able to like match up the machine learning model that we're going to be using. And so I didn't know that. I didn't really even ever think about that data has a structure. So does anyone else have any information about that? Because I would love to learn more just about the structure of data. I know we have a couple people who've been in here for a while.
I think I remember when I was first like learning about machine learning, there's I think it's with pandas or maybe it's NumPy, but there is a certain structure that you do have, and it's something to do with matrices, but I don't remember it correctly enough. But I think Andre Karpathy, he has some tutorials on like YouTube if you want to look him up, and he probably goes into more depth about them if you really want to go deep.
Andre Karpathy?
Yeah.
Cool. Can you just post his name in like the chat or something?
Yeah.
Awesome. DT, I saw you unmuted.
Yeah, so one thing about like the structure which I have like what like Chippy said, that is like, so NumPy, that's what I know, like is, as per my knowledge, it's basically your data is kind of like an n-dimensional data. So like it depends upon how many dimensions that's basically defines the structure. So it could be just a two-dimensional data where you have just rows and columns. It could be three-dimensional data where you have rows and columns and like one more dimension to, let's say, like give like some kind of additional structure like a shape to it, or like some kind of like you could say like a features or a vectors or something. So it's kind of like the dimensions keep on adding, and that basically keeps on defining the structure of the data. And lot of machine learning algorithms kind of like expect you to like flatten the data to a certain dimension so that the model trains much better. That's what I know. So even if like you have like many dimensions, you need to like kind of flatten the data in such a way that it basically helps the model basically understands the data. So that's how you kind of like restructure the data for the model, whichever you're using. So that's one thing. The reason I actually unmuted was because like when you talked about like frame a problem and get the data, I always have this question about like what you need to do first, because like if you frame a problem before, like you don't have the data, so like before understanding the data, I'm not sure like how you can achieve a goal to like solve a problem, because like whatever problem you come up with, you need to have like the justifiable data for that, or like at least a data in that format. So that's what like I usually have a question when you say frame a problem and get the data. So I usually think it's the reverse. If you have the data, then you can come up with like what goals you want to achieve through that data.
So you're saying that the problems that we're able to solve is dependent on the data we have access to.
Yeah, so if you have data, let's say only for like few parameters, like even if you have a very big, like a large, like a big picture thing or like a large problem, like you keep on framing the problem, but ultimately if you don't get the data for that problem is kind of a waste. So it's better to like see, like you could define the data, like the domain of that data, for example health data or like climate data, but then you need to get that data to specific, like to like kind of like contract or like kind of shorten the problem statement, like to make it more specific to what exactly you want to achieve as a goal.
Yeah, for example, if we have the real estate data, for example, and there's like let's just say each property has 5 features, so 5 dimensions. Would you consider that 5 dimensions?
Not exactly. I don't know exactly when do you like, because like if you say 5 dimensions, so let's say 5 features, so and you have let's say 10,000 samples, so it's kind of a 2 dimension only. I cannot exactly tell you unless I see that data and tell you that it's multi-dimensional, but I just know that it like there are some data sets, I don't know, like, but it could be like some images or like a 3D model or something, but I'm not sure exactly if I would call that data set as a 3 dimensional. It is still 2 dimensional because you have the columns as the number of features and the rows as the number of samples. So if someone could clarify like the n-dimensional thing, if they know, because I still want to read about what exactly is n-dimensional data, but I know that NumPy is used for n-dimensional specifically.
Does anyone have any thoughts on that? The dimensionality of data?
If you have 5 continuous variables for each observed house, that's definitely a 5-dimensional data set. So for example, you could have lot size, square feet, sale price, that sort of thing. And each of those is a separate dimension. They might appear in sort of a 2D spreadsheet, just like the lat long, XY, that's 2-dimensional. Those might be additional columns. The fact that you can view them in a 2D spreadsheet doesn't dictate what the dimensionality of the underlying problem is.
That makes sense. And then you said continuous variables.
Yeah.
If you've got categorical variables like a Boolean, it has a swimming pool or it does not. It has central air conditioning or it does not. So the Booleans are straightforward, but sometimes the categories take on a small number of values. For example, number of bedrooms.
Right.
And depending on how you choose to encode them, and often that's driven by the ML technique that you use, like maybe a support vector machine or a different technique. Depending on the details of how you encode them, the categorical variable might be a single Boolean variable adding just 1 dimension to the dimensionality, but you might choose to one-hot encode it. And so if it takes on 4 different values, then you might view it as higher dimensionality. That's sort of not inherent to the generative process that created that data in the world. That's an artifact of how you chose to analyze it.
I think like what continuous means, I think usually it's the time series data, right? Because that's what usually is.
Or the price of a house, that's a pretty continuous value.
Uh, yeah, but still, it like basically it needs to be like, so when you say continuous, like basically like if like even if like the price of the houses, they basically change over time. So that would automatically form a continuous data, right?
Mm-hmm.
So that's what I'm saying. Like house of like prices of the house is still a kind of time series data, right?
Mm-hmm.
Sure, that doesn't necessarily show up in your data set. Clearly it could. I tend to think of evaluating the price of a house and its nearby comps, comparable transactions. I think of that as we have a snapshot on January 1st of 2022 that this is what the neighborhood properties were valued at. And often the analysis stops there. You're right that you can look at a time series. In real estate specifically, it's not very continuous because you have these discrete sales events that let you observe the actual price of a home. And in between sale events, you're just guessing. Zillow does a good job of guessing, but it's just a guess.
Got it, yeah.
Mm-hmm. Awesome. Cool. Yeah, that all makes sense. So, yeah, so this is the checklist. I know Aditya, you said that it might not necessarily be framing the problem and looking at the big picture and then getting the data. Sometimes you get the data and the data helps you determine which problem to even frame or which problem to solve. So I guess this could be switched. But regardless, I think framing the problem and getting the data are two big steps that you have to do. You can't solve a problem with machine learning without both of these steps. So yeah, explore the data to gain insights, prepare the data, explore the different models, which one would be best, fine tune your model, present the solution, and then launch, monitor, and maintain. So regardless of whether we're working on this end-to-end project that we're starting with, or we work through the classification or neural network or whatever model we're building and problem we're solving, we're going to be working through that checklist. We're going to be doing each one of those steps each time. So, first step, framing the problem. The first thing we're asking is what the business objective is with this specific problem. So what are we actually trying to solve? Just building a model is not the end goal. We actually have to be solving a problem. How does the company expect to use and benefit from this model? Like knowing the objective is important because it will determine how you frame the problem, which algorithms you'll select, which performance measure you'll use, how to you use to evaluate your model, and how much effort you will spend tweaking it. So yeah, this is gonna basically help you create your roadmap and where you want your focus to lie, essentially, as you work through the problem. So the boss answers the model's output, a prediction of the district's median housing price. That's what we want this model to output. That's what we want it to tell us. We want it to predict the district's median house price. That will be fed to another machine learning system along with many other signals. This downstream system will determine whether it is worth investing in a given area. So it's going to help us decide whether we want to buy a house or whether we don't want to buy a house. Is this going to be an investment that's going to make us money, or is it going to lose us money? That's a pretty good goal. Getting this right is critical as this directly affects revenue. The next question to ask your boss is what the current solution looks like. So what is his vision for the future? What does he want this solution to look like? The current situation will often give you a reference for performance as well as insights on how to solve the problem. Your boss answers the district housing prices are currently estimated manually by experts, which sounds like a ton of work. So if we're able to take this manual work and automate it and allow a system to do what experts are currently doing, it just sounds like it's going to be potentially more efficient, more accurate, cheaper, and in business terms, that sounds really good. A team gathers up-to-date information about a district, and when they cannot get the median housing price, they estimate it using complex rules. Sort of what you just said, JH, what Zillow does pretty well, yeah? They must be using machine learning too, though, right? Zillow?
They'd be fools not to.
I've had access to the Zillow API, and they do actually use machine learning in there.
Nice, nice. So it looks like we have some upstream components. This is data about the district housing market. Our component is district pricing. We have our district prices. Push that into the investment analysis. There are other signals also coming into the investment analysis, and that helps us determine our investments. So this is the machine learning pipeline for real estate investments here, and we're going to dive deeper into each one of those too. I'm pretty sure this is the manual version. Like this is before actually integrating a machine learning model into it. This is costly and time. Yeah, so this is costly and time consuming, and their estimates are not great. In cases where they manage to find out the actual median housing price, they often realize that their estimates were off by more than 30%, and that's bad. So if you're able to create a model that is only off by 15%, that's just, it's not the best, but it's better than where you're at right now, and that's really the goal, right? This is why the company thinks that it would be useful to train a model to predict the district's median housing price. Given the other data about the district, the census data looks like a great data set to exploit for this purpose, since it includes the median housing prices of thousands of districts as well as other data. A sequence of data processing components is called a data pipeline.
You know, you said you made a statement. Sorry.
Okay.
Dogs are barking. You made a statement that 15% would be good, and the reality is that you have to know what margin of error actually makes for a viable business decision.
Mm-hmm.
So if they're looking at being up by 30% and they cannot forecast properly, which means they can't go forward and acquire properties in a profitable manner, or they can't get financing, whatever the problem is, you need to know what the threshold is that yields success, because a model that doesn't deliver against at least that minimum threshold is meaningless.
So you're saying that a model with a 15% margin of error could still end up costing the company more than the 30% margin of error?
It's not a question it's costing. It may make it so that it's not a viable business decision, right? If they're going into a certain market and they need a certain level of accuracy to be able to be successful there, to compete, or to just be able to function, they may not be at it now, and that's why they're commissioning this effort. But you need to know what it's going to take, what that threshold is, because that's got to be your target. At a minimum, that's got to be your target. Anything less than that, you're going to deliver, they're still not going to be viable in the marketplace.
Mm-hmm, mm-hmm.
So it's important to understand the business process and understand how they're using the data and the decisions they're making, and you know, maybe they only need to tweak it 2 percentage point, and they'll be fine. Or maybe they need to take it down to like 10% error. But until you know that, you don't really have a target.
Mm-hmm, mm-hmm. And you're determining this before you ever start building a model. You're like, hey, we can't have any higher than an 8% margin of error, or this just doesn't make sense.
Yeah, and the reason being is you may determine that the data you've got available to you is not sufficient to be able to hit that target. So there's no point spending a bunch of time and energy going out there trying to model this thing, realizing that, yeah, the shortcomings in the current decision model are not just because the process is lengthy or cumbersome, but because there's key pieces of information that just aren't there. So you'd have to go out and figure out how to source that data and bring it into your model.
Mm-hmm, mm-hmm.
But if you don't know the threshold, if you don't know your target, how are you ever going to hit it? Right?
Exactly. Yeah, that makes a lot of sense.
So a topic that we're touching on here is a cost function, where you can translate the magnitude of your misprediction error into a dollar value or something else that you care about. And so if you think about an autonomous vehicle that is trying to follow another vehicle at a 50-foot distance on a highway, you might, from your various sensors, mispredict the position or velocity of the vehicle that you're following. And it, of course, might change its velocity, and you might need to change your own to react. If you are conservatively going to err on the side of a bigger following distance, there's almost no downside. If you err by the same number of feet in the other direction and it results in a collision, well, there's several bad consequences that come from that. So in every business problem, there's always some cost function that you can tie in.
Mm-hmm. I could see things like self-driving cars not working without an extremely low margin of error as well, whereas another model might work with a 10% margin of error. It's like you want probably under even a 1% margin of error with self-driving car, for sure under 1%.
You just got to be better than people.
True. I feel like self-driving cars, though, you have higher expectations with them. Like with people, we expect people to get in 70,000 accidents a year, but one self-driving car crashes and kills someone, you hear it's like national or international news, you know?
Yeah.
They're already better than people, right?
Yeah, but like I have a Tesla, and sometimes you're driving it, and it sees something it can't figure out, and it just goes beep boop, and then you got to start driving. Which kind of takes the fun out of it. You know, you want to like be able to sleep. You know?
I think models like that, it really depends on how sensitive the sensors are and how good they are. Because those models are really taking in a lot of live data. So sometimes the sensors like do freak out. Like I had a Tesla rental in Vegas, and it did freak out a little bit when I was trying to use the self-driving. But that was because like the roads were either not lined up correctly and the sensors couldn't see the road, or there was too much data and it just got overloaded.
How long ago was that?
It was actually really recent. August? Yeah, that's when I was back in Vegas.
Oh wow. Okay.
Yeah.
Yeah, Waymo is doing fairly well. You can get a self-driving taxi in San Francisco using Waymo. Until I think last week, you could also do that with Cruise, but they have a poor safety record on the streets of San Francisco, and so they've been kicked off the streets.
I think Cruise and Waymo use a technology that's geolocated. They have to scan it in advance, and there's only certain places you can drive it. Whereas the Tesla is like just purely vision, which scares me a little.
No, they are definitely looking ahead of them, but they have different software, therefore different set of models, and the track record with Waymo is better on SF streets so far.
Ah, thanks.
I just want to point out this comment that Herschel made up here as well. We're bringing it back to the two-dimensional data set. The data points could be represented on a 2D plane with two features, so like height and weight, whereas the three-dimensional data set, you would have three features. Height, weight, and age could be represented in a 3D space. And this reminds me of a machine learning video I was watching at the gym by Andrew. He's like one of the most well-known professors in the world of machine learning. And
Andrew Ng of Stanford.
yeah, yep. And he visualized this sort of stuff with the 2D and 3D space. And yeah, that makes sense. Great course as well. So a sequence of data processing components is called a data pipeline. Pipelines are very common in machine learning systems since there is a lot of data to manipulate and many data transformations to apply. Components typically run asynchronously. Each component pulls in a large amount of data, processes it, and spits it out the result in another data store. Then sometime later, the next component in the pipeline pulls in this data and spits out its own output. Each component is fairly self-contained. The interface between components is simply the data store. The interface between the components is simply the data store. Okay. This makes the system simple to grasp with the help of a data flow graph, and different teams can focus on different components. Moreover, if a component breaks down, the downstream components can often continue to run normally, at least for a while, but by just using the last output from the broken component. Oh, so they can reuse the output from the broken component. This makes the architecture quite robust. And this kind of reminds me of just like a distributed system, but that is focused on like heavy amounts of data, and where there is a data store in between each component, where it's almost like this pipeline is receiving a ton of data, and each component is responsible for doing something to the data and then outputting the changed data. Does that sound accurate?
And it reminds me of what we were doing at my last job using S3 for storing the Amazon S3 for storing the data, where it would just be processing the old if there wasn't a new one.
Mm-hmm.
I wonder if that's what it means.
Mm-hmm. Yeah, I think that's pretty interesting. It's got to come to a point though where if it's broken for too long, then it's just, I could see that the longer it's broken, I could see it becoming worse and worse. So it's definitely something you would want to fix as soon as possible, so that I could see accuracy decreasing as time goes on with a broken component. So just something to keep in mind. On the other hand, a broken component can go unnoticed for some time. If proper monitoring is not implemented, the data gets stale and overall systems performance drops. Okay, yeah, that's kind of what I just said. So we're talking about framing our problem so far. With all this information, you're now ready to start designing your system. I feel like that's not too much information, but first determine what kind of training supervision the model will need. Is it supervised, unsupervised, semi-supervised, self-supervised, or reinforcement learning? And this stuff right here, if you don't understand these words here, these are lingo that you're going to learn in chapter 1. So feel free to either just read chapter 1 before the next meeting, or you could feel free to just chat GPT or Google it right now. Very, very simple concepts. Is it a classification task, a regression task, or something else? Should you use batch learning or online learning techniques? Again, all this stuff is chapter 1. Before you read on, pause and try to answer these questions yourself. So does anyone want to shoot and take a guess at what this model is going to be, or what would be the best for this real estate model that we're using, or that we're going to be building?
I think regression, probably. Because since we are, like, the thing about is predicting basically the house price, so regression would basically, there is no concept of classes and all. So regression would basically give that model where if you give a particular parameter, then it would actually give you the output, like kind of like an XY combination. So that's what I think.
Mm-hmm. Mm-hmm. Anyone else? So I agree with you. I think it's linear regression, and I went through this already anyways. So one thing I noticed as I went through the first time, and everyone will notice as we go through again, is that each home has like 5 or 6 or 7 features. So there's a bunch of features per home. But what I realized as I was visualizing the data and looking at it was that only 2 of the features really made a difference in being able to predict the house price. I think it was correlation. I think it was correlation that it said the correlation between only 2 features actually made a difference in the value of the homes, but the other features just were less relevant. It's not that they were entirely irrelevant, but there were 2 that just really stood out for determining the price of a home. So like you said, Aditya, it was 2 features or XY, right? 2-dimensional data.
Yeah. I mean, it's basically like you give an input, so that input would be like a set of parameters, and you would get an output. So that way, yeah. One more thing, like I'm not sure, like I haven't seen the data, but like one thing which I like thought of just bringing, like when we'll do the analysis, I don't know if that's in the book, but usually this is something which I had noticed when I had working was data. So let's say if you have like 7 parameters, and when you actually visualize the data, like one of the visualizations is better to have is the histogram to see like how many samples are those parameters actually accounting to that data. Because like I have come across this problem where I had like 3 parameters, I think no, 5 parameters, out of which 2 parameters were like, they all 5 were significant, but like 2 of them were having a data where they were like just 10% of the data, and like the other 3 were like 80% of the data. So when you have those kind of thing, I've heard this term called as oversampling, undersampling, which basically you do that. But yeah, so that's something also which usually when you do the analysis you check.
Mm-hmm. Yeah, that makes sense. And you're right, we do build a histogram here. We build a couple different graphs and a few different visualizations, so it's nice to see. It's cool when you actually map out the data points, as you all see. It's like the shape of California kind of emerges. It's kind of cool how the data does that. So let's see. This is clearly a typical supervised learning task. Since the model can be trained with labeled examples, we're passing in the data, and the label that's what we're going to be using is the actual price of the homes in our data set. Each instance comes with an expected output, the district's median housing price. It's a typical regression task since the model will be asked to predict the value. Is there anyone that doesn't know what a regression task is? If there is someone here who's like, what's a regression task? I would encourage you to go just Google it really quickly, do like a couple minutes of research, and then circle back and say, hey, I just found out what a regression task is, and just try to share it, try to articulate it with the rest of the group, and it's really going to help. So if that word doesn't make sense to you, whoever wants to go ahead and just do a quick Google search, just articulating it is going to reinforce it and help you learn it a lot quicker. So feel free to do that. I encourage anyone who's like, what is that? And I encourage you to do that with anything. As we encounter more words where you're like, multiple regression problem, what is that? I don't know. He's continuing to read and I don't know what this is. Just go Google it and then come back and say, hey, I didn't know what multiple regression was, but I just Googled it and I want to share what that is. And it's going to be good because if you don't understand what it means, there's other people who don't understand what it means. And so you're actually going to be helping out several other people in here by doing that. Also, the one who takes the initiative and goes and does the Google search and says, hey, I didn't know what this means, but I took 5 minutes and I know what it means now. Let me try to explain it. You're going to learn faster than everyone else you're sharing it with. So if there's 5 people who are like, what is multiple regression? And there's only one who's like, I'm going to go Google. I'm going to take the initiative, go Google, and I'm going to share it with everybody. You're going to learn faster than all those people you're sharing with. So just a heads up. Since the system will use multiple features to make a prediction, so we're going to be using the population, the median income, and other features like number of bedrooms, whether it's near water, and others. It's also a univariate regression problem, since we are only trying to predict a single value for each district. If we were trying to predict multiple values per district, it would be a multivariate regression problem. Multivariate regression. Finally, there is no continuous flow of data coming into the system. There's no particular need to adjust changing data rapidly, and the data is small enough to fit into memory, so plain batch learning should do just fine. So we're going to select the performance measure, and I think a few people have mentioned that already. We had JH mention that. I think Aditya mentioned that, and then one other person also mentioned, who was it? Doesn't matter, but this is just like what's the margin of error that we're looking for, essentially. So our next step is to select a performance measure. A typical performance measure for regression problems is the root mean square error. So this formula right here, it gives an idea of how much error the system typically makes in its predictions, with a higher weight given to large errors. So let me see if I remember how this worked. I believe the X is the data set and the H is the labels. And then I believe we're iterating from 1 to the length of the data set. Actually, the H is the function. The H is the actual model, I believe. And if I'm wrong, just let me know. We're iterating from 1 to M, which is the size of the data set. And then for each home inside the data set, we're passing it into this function. We're passing it into our model. And so this lowercase x is one of the homes within the large data set. And we're subtracting the label from that, and then we're squaring it. So that might be a little hard to understand, but does anyone want to add to that?
Yeah,
So
so
recall that
basically,
H-
consider it as predicted minus actual.
Say that again. I'm hearing an echo. Go ahead.
Is it clear now?
Yeah, you're good. I think you were echoing in JH's maybe.
So you could consider like the RMSE as like root of the predicted minus actual square, summation of all the predicted minus actual values square. So h of x is basically what you predict, and y is basically what's the actual value. So it's a very common I mean lot of statisticians use like just MSE, but RMSE is also like, I mean, like I have actually seen like lot of kind of like tools which basically gives you like the MSE value. So that's just removing the root. But yeah, you could consider to understand it simply, it's basically predicted minus actual value.
Yeah, that makes sense. Yeah, so the X is the actual data set, and let's just say there's 1,000 homes in our data set, then we're gonna pass in X1, X2, X3, X4, X5. So for every one of these 1,000 homes, we're gonna run this. And for each home that we pass into our model, we're gonna subtract the actual value of that home. So X1 is the features of that home, and Y1 is the actual cost of that home. And then X2 is the features of the second home, and Y2 is the actual cost of that home. And then X3 is the features or the data for the third home, and Y3 is the actual cost of that home. And so basically we're subtracting the actual cost from the features of the home, and then you said we're getting the square root of it, basically, right? Overall.
Yes.
Yeah. So there's more to it, and if you actually pick it apart piece by piece, like every time you subtract the actual value from the home, you're squaring that, and then every time you do that, you're adding it to the next one, and then the next home you're adding it to the next one, the next one you're adding it to the next one, and then you're doing the square root of all of that, and you're gonna find your margin of error. So the final result is gonna show you like how accurate your model is, essentially, right? So this equation introduces several very common machine learning notations that he'll use throughout the book. M is the number of instances in the data set you're measuring. So this M, we're going from 1 to M. So if there's 1,000, M is 1,000. For example, if you're evaluating a RMSE on a validation set of 2,000 districts, then M equals 2,000. Xi is the vector of all the feature values, excluding the label. So it includes like maybe number of bedrooms, the numerical representation of whether it's near water or not, the population of the area, excluding the label. So the price of the house in this example of the ith instance in the data set, and yi is its label, the desired output value for that instance. For example, if the first district in the data set is located at longitude 118.29, latitude 33.91, and it has 1416 inhabitants with a median income of $38,000, and the median house value is 156, ignoring other features for now. This is the property here. So we have our negative 118 is one of the features. 33 is another feature. 1416 inhabitants is the next one. Median income is the next one. So that's the actual property information. And then our Y1 would be the house value. So the value of that house right there. X is the matrix containing all the feature values, excluding labels, of all the instances in the data set. There's one row per instance, and the ith row is equal to the transpose of xi. For example, if the first district is as just described, then the matrix X looks like this. So we have our x1, x2, ... all the way to x1999, and then x2000. And each one of these x's, x1, x2, x1999, they each contain all of these features here. So H is your system's prediction function, also called a hypothesis. I believe someone told me that this is our actual model. When your system is given an instance's feature vector xi, its output is predicted value. It outputs a predicted value yi. So H, the function, you're passing in xi for that instance. Y is pronounced y hat. For example, if your system predicts that the median housing price in the first district is $158,400, then y hat 1 equals our hypothesis function with x1 passed in equals 158,400. The prediction error for the district is y hat 1 minus y1, so 2,000. So 2,000 off. Root mean squared error. xh, so this here, is the cost function measured on the set of examples using your hypothesis. So it's just a function that helps us determine the margin of error on our current model. We use lowercase italic font for scalar values such as m or yi, and function names such as h, lowercase bold font for vectors, and uppercase bold font for matrices. So that's something to keep in mind as we work through all this stuff. And then, although RMSE is generally the preferred performance measure for regression tasks, in some contexts you may prefer to use another function. For example, if there are many outlier districts in that case, you may consider using the mean absolute error, also called the average absolute deviation. And I believe that this function here, this cost function, is actually going to reduce the error on the same data set to account for outliers that are included in your data set. Before we keep going, we're going until 7:30 today, so I'll go ahead and read through just the mean absolute error, and then next week, or even check the assumptions. We'll just go all the way up to check the assumptions to get the data. That way next week we could just start typing some code. Yeah, I'll just run through this really quickly, and then we'll just have a quick chat before we sign off, and everyone could feel free to just hang out and chat about anything after the meeting as well. So this is the other error this is the other cost function that's going to minimize the error. So if like the error that we're getting on this root mean squared error is just too large, or we have a couple outliers that are negatively affecting the results, then we could use this one here. But like it said, this one is not typically used. Typically we would use this one, and if we are getting a large error, then we would modify the data in a way that minimizes the error to create a more effective and accurate model. Both of these are ways to measure the distance between two vectors, so the vector of predictions and the vector of target values. Various distance measures or norms are possible. This is very, this is technical stuff, so I'm not going to read that. We'll just skip over since it's less commonly used. The higher the norm index, the more it focuses on large values and neglects small ones. This is why the RMSE is more sensitive to outliers than the MAE. But when outliers are exponentially rare, like in a bell-shaped curve, the RMSE performs very well and is generally preferred. Lastly, it's good practice to list and verify the assumptions that have been made so far by you or others. This can help you catch serious issues early on. For example, the district prices that your system outputs are going to be fed into a downstream machine learning system, and you assume that these prices are going to be used as such. But what if the downstream system converts the prices into categories, cheap, medium, or expensive, and then uses those categories instead of the prices themselves? So this would be more of categorical than continuous, I believe. In this case, getting the price perfectly right is not important at all. Your system just needs to get the category right. If that's so, then the problem should have been framed as a classification task, not a regression task. Gotcha. You don't want to find this out after working on a regression system for months. Yeah, so what do we want the output to be? Do we want our model to say, hey, this is a cheap home, this is a medium home, this is an expensive home, or do we want it to show us the actual value of the home? And if it is going to be categorical, cheap, medium, expensive, then it's going to be a classification task instead of a regression task. This one we're doing here is going to be a regression because we're actually predicting the cost of the home. Fortunately, after talking with the team in charge of your downstream system, you're confident that they do indeed need the actual prices, not just categories, and we are ready to go.
Once you've boiled it down to categories, you can't come back, so you're better off with the regression.
Yeah, so that's that. Next week when we meet, we will start actually coding this up. So the first thing we're going to do is there's a Google Colab that if you don't have the code editor or don't want to work through the code editor, you could work through the Google Colab. And there's a Jupyter Notebook, so you could actually just run it right there in the Jupyter Notebook. It makes interacting with the code a little bit easier. I'm going to go ahead and actually type the code out. I like to just get my hands dirty with it. And then, yeah, so this next section, I would say for next week, we're going to be getting the data. So we're going to be importing the data into our code editors. For those who want to be set up and ready to go, just download PyCharm or the code editor of your choice. And I would say read through. I'm not going to read through setting up your Google Colab. I'm just going to expect everyone to either have their Google Colab set up or have their code editor set up so they can start typing the code. And then we'll download the data. We'll jump straight to downloading the data. And this is just some of the code we'll be writing. This is loading up the housing data. We're pulling it from this URL here. So, yeah. Then we'll go from there. Thoughts, comments, questions?
So the choice of an error measure didn't seem especially well motivated. I just wanted to remark on that. In this domain, probably the MAE would suffice because you care about the total magnitude of the bad investment choices that you made when buying and selling homes. In a physics domain, for example, if you are trying to maintain constant temperature by heating a resistor and there's measurement errors and prediction errors, in a physics domain, that will often motivate RMS error because root mean square is identical to the power that you spent. And so if there was an error where you heated too much or too little, and what you care about is my energy costs over that interval, then RMS would sort of naturally fall out of the physics.
That makes sense.
Yeah, I mean, there are like multiple error measures which I know. I think chi-square is one of them, right? Like there are like various error measures which usually are used for data. RMSE is one of them, but like RMSE I think is not like the perfect one. There are like really good error measures which we can like use, but I'm not sure like how it like how you choose a particular error measure. So that I'm not sure exactly.
I will I'm just gonna do a quick little search and check that out really quickly.
So you can have prediction errors that are small or big, and RMS makes big look even worse. It magnifies how much you care about big errors. So in the real estate domain, maybe we figure that house prices are inherently noisy. Not even a human expert can get within 1% of predicting an actual sales price. And so RMS might be saying, a little bit of noise, as long as you're close enough, that's okay.
Yeah, this is saying that the mean absolute error is suitable when all errors, regardless of the direction, positive or negative, are equally important, and it's less sensitive to outliers compared to methods that square the errors. The mean root squared error, it's sensitive to larger errors and outliers, often used in regression problems, especially when the distribution of residuals is Gaussian. I'll have to look more into that too. And then, yeah, you're right, Aditya, there are tons of different cost functions, not just these two.
So sometimes physics motivates RMS, sometimes human psychology motivates RMS. If you look at people waiting for a bank teller or any other queuing situation, you might want to tolerate small delays, but get really upset about large delays and have your system respond very strongly to those. And so again, RMS can be helpful there, where the usual 1 or 2 minute wait, nobody really bats an eye, but when it starts to get to 10 or 30 minutes, then they will abandon the system, change their behavior, and so your cost function might reflect human psychology.
Huh, that's interesting. Yeah, you're right. It does say the context of the problem makes a difference. Huh, interesting. Cool, cool. What else?
I had sort of a leftover remark. So you talked about categorical, where we can do a regression and then discretize to high, medium, low. I found it interesting that the cost function in the problem statement was using a robust statistic. It was using median home price predicted rather than the average home price. And of course, that task that we put on the model reflects how the existing marketplace prefers median over average. The difficulty with average is you have a few mansions, and every single dollar of sale value is going to move the average, but it'll have zero effect on the median. And so we can worry about, are there outliers, the Y, in the actual data, like mansions. But we can also worry about, are there outliers, the H of X, the predicted value. And sometimes our model happens to just kind of go crazy because it behaves oddly when it's near water or something. And only a small percentage of homes are near water. And so the fact that we're not paying attention to the average predicted price, but rather to the median by district, where there's more than 100 homes in each census district, I found was sort of interesting. It makes it an easier modeling situation.
Yeah, we're going to encounter some of that stuff with this problem as well. There are certain districts that have like cost control. So all of the properties are like $350,000 each. And I believe we cut that out of the data, but I'm not positive. I forget.
I think there are some visualizations which basically helps you like identify the outliers. So I think it's basically you kind of distribute the data along the median, all the data points, and you use your predicted minus actual value around a median, and then you find like some points which are being like way away from the median. I don't know the term. It's kind of like a stats term for it, but that helps you detect the outlier points. And since it's a discrete data, you can actually like remove those points.
So beauty is in the eye of the beholder. So are outliers. It all comes down to what you're trying to accomplish. One of my favorite definitions for an outlier is that there's a generative process in the world. People engage in economic activity, they build and purchase homes. There's a generative process that we observe, we see the sale price. And then there's another generative process. For example, you mentioned this legislative process that imposes caps in certain districts. And so my preferred definition for outlier is that it was a different generative process that produced that observation. In other words, there's two different processes in the world. We're thinking about economic and legislative, and one process explains some of the observations, another process explains the other observations. And if they're the minority, then it may be convenient to say, oh, we don't care to model that at all, and we're going to discard those observations.
Yeah, that makes sense. Cool. So it is 7:35 right now. I'm gonna hop off. I have a training I'm giving at 8 o'clock, so just unwind for a couple minutes. Feel free to hang out and just continue chatting or discussing anything machine learning or otherwise. It doesn't have to be machine learning. Hang out and just chat if you want. And we will be meeting back here next Wednesday, 6 p.m. Eastern Standard Time, and we'll keep going. Yeah. So if you, like me, I'm going to continue reading the book throughout the week. I'm on chapter 3. I'm working through the classification stuff. Feel free to continue reading and sharing what you learn throughout the week as well. Like I said, if you scroll down just a little bit, we have a machine learning channel. So as you're learning throughout the week, feel free to keep the conversation going too. And reach out to me if you have any questions, concerns, or just want to say hey. Have a good night, everybody.
Cool. Thank you.
Thank you.